Hello and welcome to Week 11, Part 6 of EGM310, Accuracy Assessment. In this lesson, we will learn about how we can evaluate how well our classification has done in identifying objects and surfaces in images. To be useful, we need to have an understanding of how accurate our classification is. Any classification is going to have errors, but whether we can trust the results and whether we can use them to draw conclusions about what it is that we're studying depends on being able to quantify and understand those errors. We have a number of different ways that we can try to evaluate a classification, but perhaps the most common method works as follows. First, we take a random sampling of points within our study area. Typically, we want to sample around 1 to 2% of the pixels in an image. We can then look at each of these points and determine which class they should belong to. If we can, we might also go and check these points in the field in a process known as ground truthing. Finally, we compare the results of our manual classification with the results of the automatic classification and calculate the error and uncertainty. When we do this comparison, we most often use something known as a confusion matrix. I've seen these displayed in a couple of different ways. Sometimes you might see the true values or actual values up here as the columns and the classified values are in the rows, or you might see it as I've shown here, where we have the columns moving this way representing how the pixel was classified by the computer, and the rows moving down representing the actual or true class values for a given pixel. So as we move across the top row here, what we see is that we have pixels that belong to the A class, that is, they have an actual value of A, that the machine has correctly classified as belonging to A, labeled true A. We have pixels that were incorrectly classified as B, and pixels that were incorrectly classified as C. And we have equivalents for the B class and C class as we move down the table. The overall accuracy, that is, the percentage of our sample pixels that were correctly classified by the computer, is the sum of the diagonal values. That is the true A, true B, and true C, divided by the total number of sample pixels. This is one way of reporting the accuracy of the classification, but it is not the only way. For instance, it doesn't tell us anything about the pixels that were incorrectly labeled as a different class, the false B and false C pixels in the row up here. This is what is known as an error of omission. The classification has omitted these or left them out of the correct class. It's also known as a false negative or a type 2 error. We can calculate the error of omission for our A class by adding the number of false B pixels to the number of false C results in the top row here and dividing by the total number of pixels that should have been classified as A. And we can do this for the other classes as well. A second type of error that we might want to know about is what's known as an error of commission. That is, pixels that have been incorrectly included in the wrong class. These are also known as false positive results or type 1 errors. The way that we calculate this for the A class is by taking the pixels that should have been classified as B but were instead classified as A, and adding those to the pixels that should have been classified as C but were classified as A, and then dividing by the total number of pixels that were classified as A in the image. Next up, we have the producer's accuracy. This is the probability that the class has been correctly classified. In other words, it tells us how well our classification scheme has done classifying a particular class. This is calculated as either the number of correctly classified A pixels, the true A, divided by the total number of pixels that are actually A, or it is also 1 minus the error of commission. So you see here we have, the error of omission. We have 1 minus the producer's accuracy gives us the error of omission. Finally, we have something called the user's accuracy. This is the probability that a given pixel on the map has been correctly classified. In other words, it tells us how well we can trust that the classified map actually represents the truth. We can calculate the user's accuracy as the number of correctly classified A pixels divided by the number of pixels that are classified as A, or as 1 minus the error of commission. Again, you can see the relationship here. And we do this for each of the classes that we have included in our map. This doesn't tell us everything, though. It's possible that our classification only looks good because of random chance. It doesn't mean that we've done a good job classifying the image, it just means that we got lucky. One way that we can check this is by calculating something called a Kappa coefficient, or Cohen's Kappa coefficient, or sometimes just Kappa. Whatever you call it, this is an indicator of whether the accuracy is due to a random chance or not. It's calculated by subtracting the probability of chance agreement from the observed agreement and dividing by 1 minus the probability of chance agreement. And of course, we can calculate the probability of chance agreement as just the sum for each class of the percentage of our sample pixels that belong to that class times the percentage of our sample pixels that are classified as that class. We'll work out an actual example on the next slide, so don't worry too much about this just yet. Kappa typically has values between 0 and 1. We can have values less than 0, but this is really bad. This means that our classification algorithm has done worse than random chance. Not a good sign. If Kappa equals 0, it means that we haven't done any better than random chance. Again, not a great sign. It suggests that our classification isn't particularly reliable. Values greater than about 0.5 are considered moderate or good, depending on how you talk to. To put this another way, a value of 0.5 means that we've done 50% better than we would expect by random chance alone. This is a lot to take in, so I'll try to go through a worked example. To make the maths much simpler, I'm sticking to two classes, land and water, and say that we've drawn a sample of 30 pixels from both land and water. From our confusion matrix, you can see that we've correctly identified 24 pixels as water and 21 pixels as land. So our overall accuracy can be calculated as 24 plus 21 divided by 30 plus 30, or 0.75. An overall accuracy of 75% is generally considered acceptable to good, again depending on who you talk to. Next up, let's calculate the user's accuracy. For water, this is the number of correctly classified pixels, 24, divided by the total number of classified pixels, which is 33. 24 divided by 33 gives us 0.73. For land, this is 21 divided by 27, which gives us 0.78. This tells us that a pixel on the map that is classified as land is slightly more likely to be correct than a pixel classified as water. To calculate the producer's accuracy for water, we divide the number of correctly classified pixels, 24, by the number of sample pixels, 30, to get 0.8. For land, we have 21 divided by 30, which is 0.7. So this means that we're doing a slightly better job classifying water pixels than we are land pixels, but with the user's accuracy that we calculated, we can also see that we have a higher rate of false positives for water. To calculate the Kappa coefficient, we can start with the formula that you see here. For water, the chance agreement is the percentage of our sample pixels that are actually water multiplied by the percentage of our pixels that are classified as water. So the percent that is actual water is 30 divided by 60, because that's 30 and our total number of sample pixels is 60. And the percentage of pixels that are classified as water was 33, again divided by 60. The percent actual land is also 30 over 60. We have a balanced sample. And the percent classified as land is 27 divided again by 60. So if we put all of this together, So we have 30 divided by 60 times 33 divided by 60 plus 30 divided by 60 times 27 divided by 60. We should get 0.5, which is to say that we have a 50-50 chance of correctly identifying a pixel based on the sample that we've drawn. If we then plug this into the formula for kappa, we take the overall accuracy, which is 0.75, remember, minus the chance agreement, 0.5, divided by 1 minus the chance agreement, 0.5. And if we do all of that, we should get a kappa value of 0.5, which is, remember, saying that our classification scheme is 50% better than what we would expect by random chance alone. So this is a moderately successful classification. Hooray! In this lesson, we have learned that accuracy assessment is the key to understanding how reliable our classification is. If we don't know how good a job we've done in our classification, we can't know how useful our results are. To do this, we compare our classified image to either ground truth data that we've collected in the field, or by manually classifying test points or test regions in our image. Often, we might want to use a combination of these approaches. We also want to assess both the overall and by class accuracy. This can help us to understand where we might need to improve our training samples or our input data in order to help improve the classification. Finally, we learned how to compare our results to the likelihood that our results are due to random chance by calculating the kappa coefficient. Once again, you can read more about these concepts in the textbooks, Chapter 7 of Lillesand, Kiefer, and Chipman, and Chapter 14 of Campbell and Wynne. I've also included links to information about performing accuracy assessment for both of the two software packages that we've used in this class, ArcMap and Erdos Imagine. You can also look in the practical documents for more instructions. There's also a link to a shorter video that shows you how to do this in Erdos. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!